Good morning, everyone. Today we are going to continue our talk about corrosion and degradation of materials. This is the third part of this topic. And I'm going to talk, today we are going to learn the passivity and also learn the forms of corrosion. And in last time, we talked about the standard EMF series. Can some guy told me about the EMF? Does the EMF stands for? EMF here stands for electromotive force series, or this is standard or this is electrochemical series. And so it is the indication that and how easily this guy can be can corrode. And you can see here, so this is the table, and you can see these are two different colors, the arrows here. So if going up, it means more cathodic, and going down means or more anodic. So metal with smaller, this is standard EMF series. This potential we call this a standard electrode potential. Metal with smaller V corrodes. And for example, for this CD and Ni cell, CD stands for cadmium, Ni means nickel. If we connect these two cells, and because VCD is less than VNI, and as a result, VCD will corrode, and Ni, CD will corrode, and Ni will be gaining new atoms, and we call deposition. And you can see this is this picture. So this CD at the very beginning, this CD sample has regular the boundary, but now you can see we have as the time goes, and so this guy here has irregular surface, and all this is the atoms, and they become ion and dissolve in the solution, and also at the same time, and they give up these free electrons, which come through this wire to this half of the cell, and then these free electrons will be obtained by the nickel solution, nickel ions in the solution, and then these nickel ions will become the nickel atoms, and then the newly developed nickel atoms will be deposited on the surface. As a result, we have an irregular surface on the nickel the sample. So this is how to explain this diagram. And we also talk about the corrosion in a grapefruit. And so here, okay, so here is a copper cathode, and the zinc is anode. And so here, zinc anode and zinc corrode, and zinc corrodes. Corrodes means that the zinc experiences oxidation by giving up these free electrons and then become the ions. So this is reduction. Here at this side, we have this hydrogen ion. Okay? Hydrogen ion will obtain these free electrons. So one hydrogen ion will obtain one free electron, and then become a hydrogen atom, and two hydrogen atoms will form one hydrogen molecule. And so this molecule, they will become, when they come together, become a bubble. So this is the oxidation reaction. So this is reduction reaction. So you can see here, this is what I just told you. Gas here, you have this hydrogen gas, and then this oxygen here, and oxygen and plus this is the 4H ions, and then along with 4 free electrons, and they can become 2 water molecules. So this is acid. Any questions regarding this slide? And then we talk about galvanic series. The ranking of the reactivity of metals alloys in seawater. And so here, and so this is more cathodic, and so also this is more anodic. And so we have different materials here. So that means this magnesium and it is very easy to corrode. And on the contrary, platinum is very inert when in the water. And gold, graphite, titanium, silver, 316 stainless steel, and also nickel, copper, and nickel is active. This is a standard EMF series here. So this shows more anodic, and more cathodic. And then we talk about passivity. And what is a passivity? And passivity means some normally active metals and alloys lose their chemical reactivity and become extremely inert. So this is how we define passivity. This behavior is displayed by chromium, iron, nickel, titanium, and their alloys. So this behavior results from the formation of a highly adherent and very thin film on the metal surface, which serves as a protective barrier to further corrosion. And any questions regarding this slide? Let me tell you one thing, passivity, okay? I want to refresh you, reinforce your understanding of passivity. It means that some normally active metals and alloys lose their chemical reactivity and become extremely inert. And so this is how we define passivity. And this behavior is displayed by these examples. This is example alloys and metals and metal alloys. And then what is the mechanism? How can these materials achieve passivity? And I might ask you questions in our following quiz or following exam. So that's the reason I want you guys to understand this slide truly and fully. Questions regarding this slide? And then we talk about passivity, and this is a schematic polarization curve for metal that displays an active and passive transition. So here, this is electrochemical potential V. Okay, this is the V, also called standard electrode potential. And so here's a log current density I. So this is the V here. So this is M. Okay, this M becomes M ion plus 2 free electrons. So what would call this is a oxidation. And so here, this is I0 have a current here. So this is active, and in this area, and this active. Do you understand? In this area, the current increases, and so from 0 to this bar, we call this active zone. From this bar to this bar, and we call the passive zone. For the passive zone, that means the I does not change. I remains the same, even though you increase electrochemical potential V. And above this is a dotted line, and we call transpassive. So this is a schematic polarization curve for metal that displays active and passive transition. Any questions regarding this slide? And then we talk about how an active passive metal can exhibit both active and passive corrosion behavior. So here is the electrochemical potential. So this is the V, okay? So this is I0, this I0. This is for one case one. So this is a case two. This is log current density. So you can hear. And so from here, the log density, if we have this I here, okay, have I here, it goes here and come to this. This is the curve. This is a straight line. And also this one is a straight line. And then we talk about environmental effects. And the fluid velocity is the fluid velocity. And temperature, definitely. And composition of the material. And cold worked metal is more susceptible to corrosion than the same material in a nude state. And be very, very careful. Okay, so cold worked metal is more susceptible to corrosion than the same material in a nude state. And then we talk about the forms of corrosion. So first one is a stress corrosion, and corrosion at crack tips when a tensile stress is present. The crack tips when a tensile stress is present. Stress corrosion. So erosion corrosion combined chemical attack and mechanical wear. For example, the pipe elbows. Erosion corrosion. Erosion is mechanical, corrosion is chemical. Pitting, the downward propagation of small pits and holes. Look at this. This is example. Pitting. So crevice, narrow and confined surface. Narrow and confined surface. So this is crevice. Galvanic and dissimilar metals are physically joined in the presence of electrolyte. And the more anodic metal corrodes. This is what we just talked about. This is when we connect the two things together and two electrodes together, and then we will have the current there. And one corrodes, another one, and we have deposition on the surface. Galvanic and irregular corrosion. This irregular corrosion along grain boundaries, often where precipitation particles form. Look at here. Grain boundary, precipitation. So this is one grain, one grain, one grain. So this attack the zone. This zone is attack zone. And selective leaching. Unpreferred corrosion of one element or this constituent. For example, zinc from brass. This is selective leaching. I just want to eliminate one single element or constituent and get another one. And uniform attack, oxidation and reduction reactions occur uniformly over surface. So this is the forms of corrosion. And then we know that corrosion is bad for the economy, and every country, almost, I think, not almost, every country does not want to have corrosion, right? Because corrosion will affect the economy very, very substantially. We lose a lot of money without doing anything. And how to prevent corrosion? There are several ways to prevent. And first one, material selection. For example, use metals that are relatively unreactive in the corrosion environment. And for example, select nickel in basic solution. Basic means that a basic solution means that this solution has OH ion. And second one is use metals that passivate. Use metals as passivate. So these metals form a thin adhering oxide layer that slows corrosion. So metal oxide, this is metal oxide, this is metal, and then because this metal oxide is a very, very thin layer, adhering layer, so the oxygen will not come through this metal oxide layer to reach the material here, and to that result, this is oxygen cannot cause further corrosion. So, for example, aluminum and stainless steel. I want you guys to know this because this passivity can help us a lot, substantially. So one example is that aluminum. So when I was young, when the new year came, and we always wanted to just polish the aluminum alloy pots, and to make sure that to want to show people that, and so everything is clean in my house. But at that moment, I have not learned this knowledge. So I help my dad clean the pots outside. So when I learned these things, I stopped helping my dad. I told my dad that don't just polish the metal oxide, aluminum oxide layer away. And otherwise, if you polish this aluminum oxide layer away, and then the new aluminum alloy material and will touch the oxygen, surround oxygen, and then we will have another layer of metal oxide. And if you keep polishing this is metal, this is aluminum parts, and they will become thinner and thinner and thinner. Finally, it just break. So this is how we can use the knowledge in our daily life and to improve our life quality. Any questions? And another one is lower the temperature. We know that at the temperature, if we increase the temperature, and we can accelerate oxidation and reduction. And then we go in the opposite direction, lower the temperature, and then we can reduce the rates of oxidation and reduction. Another way is apply physical barriers, for example, films and coatings. And by you doing this, we can physically just separate our materials from the from this oxygen in the surrounding area. And another one is add inhibitors. So inhibitors is the external substance material, and substances added to solution that decrease its reactivity. And for example, on slow oxidation reduction reactions by removing reactants. For example, remove oxygen gas by reacting it with a inhibitor. Right? If this is oxygen gas and they just react with the ended inhibitors, so this is we will not have oxygen. Well, I should not say not have. We will minimize the level of oxygen that can react with our material. So second one is a slow oxidation reaction by attaching species to the surface. So another way to stop oxygen from reaching our material. Next approach is cathodic protection, or is a sacrificial protection. attach a more anodic material to the one to be protected. And then if we do this, the more anodic material and will be oxidized, will corrode, and our material will be protected. For example, galvanized steel here, zinc, and this is and steel, zinc coated nail here. Okay, zinc, and this is steel here, galvanized steel, and using a sacrificial node and a steel pipe, and we don't want this steel pipe and to be corrode, and so we want to use a sacrificial material. In this case, we use magnesium. I told you guys magnesium is in that slide. Magnesium has lowest EMF standard electrode potential on this EMF series. So as a result, this Mg will give up electrons. So these free electrons will come to the steel pipe. And so as a result, so the steel pipe will not corrode. Corrode means that the material give up electrons and become an ion from atom. Right? So any questions regarding this slide? And corrosion of ceramic materials. Corrosion of ceramic materials being inherently corrosion resistant are frequently used at elevated temperature and or in extremely corrosive environment. This is very beautiful properties of ceramic materials. And then we talk about the degradation of polymers. Right? Polymeric materials deteriorate by non-corrosive process. It's different from what happened to the metals and metal alloys upon exposure to liquids, and they may experience degradation by swelling or dissolution. So with swelling, solute molecules actually fit into the molecule structure, swelling. Okay, dissolution may occur when the polymer is completely soluble in the liquid. Dissolution dissolves. So scission or the severance of molecular chain bonds may be induced by radiation, chemical reactions, or heat. So this results in a reduction of molecular weight and deterioration of the physical and chemical properties of the polymer. So let's summarize what we have learned, not just for today, but also for the recent several class sessions. Metallic corrosion involves electrochemical reactions. One corrode, another one experiences the reduction action. So electrons are given up by the metals in an oxidation reaction. So these electrons are consumed or obtained in the reduction reaction. So metals and metal alloys are ranked according to their corrosiveness in standard EMF standard for electromotive force series and galvanic series. So temperature and solution composition affect these corrosion rates definitely. Temperature and this solution composition and how the composition, or we can call concentration, and the forms of corrosion are classified according to mechanisms, right? Different mechanisms and different ways we call mechanisms. And corrosion may be prevented or controlled by material selection, reducing the temperature, applying physical barriers, adding inhibitors, cathodic protection, sacrificial protection, and corrosion of ceramic materials and degradation of polymers. I need to tell you guys, ceramic materials are usually very stable, but right, ceramic materials are very stable, and degradation of polymers, ceramic materials and polymers, and they have their own different mechanisms of corrosion. We call corrosion or call degradation. But for polymers, we usually call the degradation. Any questions regarding this slide? Okay, guys. Up to now, we have talked about all the important topics in material science. And next class, I'm going to review all these lecture notes, review all this knowledge, and we have learned. Thank you very much.